Do you know what these three things are? Protons, neutrons, and electrons. Hi everyone, I'm Mr. Pinola. Today we're going to take a close look at these three things. But what are they? You might be saying, well, I know that one of them is positive, one of them is negative, and maybe one of them is neutral. In science, we call these three things subatomic particles. Subatomic particles, what does that mean? Well, if you look closely at the word, the prefix sub means inside. You can think about it sort of like a submarine would be inside the water, or something that is subterranean would be inside the earth. So if something is subatomic, it would be inside an atom. These are the three particles that make up atoms. They are the tiny building blocks that create atoms, and atoms make up pretty much everything else in life. So now that we know what these subatomic particles are, they are the things that make up an atom, we should find out a little bit more about them. Now, you might already have heard that protons are positive, electrons are negative, and neutrons are neutral. And I'm going to write the number 0 to represent neutral. But positive, negative, and neutral what? Well, we're talking about something that is called charge. And the concept of charge is kind of a mystery to scientists. We know, though, that it is a property that these subatomic particles have that cause them to either attract or repel each other. Now, you might be looking at this saying, well, positive and negative, I know what those are, but what does it truly mean to be neutral? Well, that means that the neutrons have no charge and they will not attract or repel. So let's cross them out for today because we're going to only focus on the subatomic particles that are charged. That is, the positively charged protons and the negatively charged electrons. Let's now consider a single proton, sort of like the one I drew on the board. Now, this proton is not even close to the actual size of a proton. An actual proton is microscopic. Your body is made up of billions and billions of atoms, and each of those atoms has a lot of protons in it. So they are so tiny that humans can't actually see them with our naked eye. However, we are going to kind of blow it up and treat this dot as a model of a proton. Now, we said that protons are positively charged, but what exactly is the charge on one proton? Many people might say the charge in a proton is +1. But +1 what? We as scientists know that we need to have a unit for pretty much every value that we speak about. Well, +1, this doesn't have a unit associated with it. We need a unit to measure charge. And so even though we know that a proton is going to have a positive charge, we need to be specific about the units that we're going to be measuring that in. The units to measure charge are coulombs, which is symbolized by a capital C. I'll put that in parentheses down below. C-O-U-L-O-M-B-S, coulombs. You can have a charge of, let's say, 5 coulombs. It's a unit that was named after Charles Augustin de Coulomb, who was a French scientist. Now, let's get back to that question at hand. What is the charge on a single proton? Well, you might think that it's +1 coulombs, but you'd be wrong. The charge on a single proton is actually +1.6 times 10 to the -19th coulombs. 1.6 times 10 to the -19th coulombs. Is that a big number? No, this number is tiny. 10 to the negative 19th. That's like a decimal point and then a ton of zeros before we got to the 1.6. So in other words, I'm not going to go through and write out all the zeros. This is a very, very small number. That means that 1 Coulomb is actually a lot of charge, and that would be a lot of protons put together to make up a single Coulomb. So hopefully now you see that coulombs are the unit that we as scientists measure charge in. And 1 Coulomb is actually a lot of charge because protons carry only 1.6 times 10 to the negative 19th coulombs for each one of them. So if this is a proton, let's now draw an electron. It almost looks like my drawing's incomplete, but it's true. Electrons compared to protons are much tinier. They have a much, much, much smaller mass. Now, this still isn't close to the size of an actual electron. This is just a model. An actual electron is super tiny, even smaller than protons, which we already couldn't see. But do you know the charge of an electron? Well, we know that they are negative. But negative, how many coulombs? Remember, we have to use that Coulomb unit to express amounts of charge. Well, each electron is actually going to have negative 1.6 times 10 to the negative 19th coulombs of charge. That's right. 1 proton has positive 1.6 times 10 to the negative 19th coulombs, and 1 electron has negative 1.6 times 10 to the negative 19th coulombs. A negative amount of this really small amount of charge and a positive amount of this really small amount of charge. That means if you put a proton and an electron together, you would have no charge because they would cancel each other out. One would be positive, one would be negative, and overall there would be no charge. So let's say that we had an atom in it, or an atom that inside of it had 5 protons, which I'll show with a positive sign, and 3 electrons. Do you know what the charge on this atom would be? Well, it's really important here that we not just find the charge, but we find something called the net charge. Or in other words, the overall charge. Since there are 5 protons and 3 electrons, there are 2 extra protons. And so I'm going to write that here in red. There are 2 extra protons. So to truly find out what the net or the overall charge is, all we have to do is just consider the 2 extra protons, because the other ones will have canceled out. So what are the charges? What is the total charge on 2 protons? Well, all we need to do is do 2 multiplied by the charge on a single proton, 1.6 times 10 to the negative 19th coulombs. If I do that math out, I will find 3.2 times 10 to the negative 19th coulombs is the net charge on this atom. Many people will simply refer to the net charge as positive 2. But we know if you were being asked to use units, that positive 2 corresponds to 3.2 times 10 to the negative 19th coulombs. 2 extra protons would carry this much of an actual value of charge. So when you find the net charge on something, consider how many protons there are, consider how many electrons there are. Figure out which one of those 2 you have extra of, and then figure out the amount of charge that would correspond to that many extra subatomic particles. Did you know that scientists have a name for an atom that's like this? An atom that has more protons than electrons? Or the same name would apply to an atom that has more electrons than protons. Basically, scientists have a nickname for anything that carries an overall net charge, meaning that if there is an imbalance in protons and electrons, that we have what's called an ion. And an ion is very simply a charged atom, or an atom that has a net charge on it. If you have an atom that has unequal numbers of protons and electrons, it means it has a net or an overall charge, and it should be considered an ion. If, however, the atom has equal numbers of protons and electrons, unlike this example I drew on the board, then the atom would be considered just a neutral atom. It would carry no electric charge, and therefore it would not be considered an ion. So what do charges do? Well, maybe you have heard the common expression that opposites attract. Well, that applies to charges. Two opposite charges, meaning positive and negative, will attract. They'll be drawn towards each other. And similarly, scientists say that likes repel. Like meaning alike or the same, and repel meaning push away. So if we have two like charges, meaning we have two positive charges, they will want to push away from each other. And if we have two negative charges, they will also want to push away from each other. Opposites attract and likes repel. Let's see an example of this. Here is a proton. It's positively charged. Here is another proton. It's positively charged. Do you know what these two particles are going to do? That's right. They are the same. They are going to push away and repel because they're the same charge. However, let's consider a slightly different example. Let's say I had a proton and an electron. What would happen to these charges in the purple, assuming that they were separated and far away from the charges in the black? Well, they would actually be attracted towards each other, and they would feel an electric force bringing them closer together. And that's because opposites attract. The last possible combination we could have is if we had two negative charges, such as two electrons. If we think back to our rules, these charges are alike, and they will repel as well, just as the two protons in my earlier example did. So now let's zero in on that first example. Here are two positive charges. We know from our rules that these two positive charges will repel or push away from each other. But what could cause them to want to push away even more and with a stronger amount of force? Well, one thing that could happen is if the charges themselves were stronger. Right now, I just put one positive sign on each one. But let's say that this charge on the left actually was made of 4 protons. And the charge on the right was made of 2 protons. Now these charges are going to push away much more than they did before. That's because we have stronger charges, positive 4 and positive 2. Since the charges are bigger, the repelling force between them will be much stronger. But what happens if I can't change the number of protons or electrons in an ion, meaning that I'm locked into having a charge of +1 and +1? Can I still make it so the charges will repel each other with more force? You betcha. I definitely can do that. The way I can do that is I can actually bring them closer together. Think about if you've ever taken two magnets and brought them closer together. The closer the magnets get, well, they'll either push away with more force or they'll quickly grab onto each other and attract with a really strong amount of force. When you make the distance between two charges smaller, the same thing happens. They will repel with more force or attract with more force if the charges were opposite than they would have before. So this example that you see here would not generate much force between them. But if the charge on the left were moved just a little bit closer to the charge on the right, then they would repel with even more force. Not because the charges were any different, it's still +1 and +1, but just because I've cut down on the distance. So we just noticed that there are two factors that affect the electric force that exists between two ions. In other words, there are two things that we could change that could cause two ions to attract or repel each other with a stronger amount of force. The first thing is the amount of charge. If an ion has more charge, for example, +5 versus +2, it will attract or repel in a stronger way. So we say that the amount of charge has a direct relationship with electric force, meaning that as the amount of charge goes up, the electric force will go up as well. Remember, if two factors go up together, that's a direct relationship. More electric charge, more force between the ions. But what about the second factor that affects electric force? We said that that factor was distance, or more specifically, the distance between the two charges. This factor has an inverse relationship with electric force. And that's because as you make the distance between two charges bigger, as you pull them further apart, so distance goes up, the amount of force between them goes down. They will not repel as much, and they will not attract as strongly either. That's an inverse relationship. Distance goes up, force goes down. There was a scientist back in the 1700s who first made these big discoveries. The fact that if the amount of charge in an interaction between two charges goes up, that the force will go up, and that if you increase the distance, the force will go down. Do you know this scientist's name? Well, I've actually mentioned him already today. The scientist is Charles Augustin de Coulomb, and this is known as Coulomb's law. Coulomb, who not only has the unit of charge named after him, also is the man who is credited with discovering the fact that if you have two charges and you are looking for the strength of the force between the two charges, that if you make the charge bigger, they'll attract or repel with more force. And if you pull them apart, they will attract or repel with less force. Coulomb had some big impact on electricity. Let's take a look now at one final example. On the board, I've drawn up a very, very positively charged ion. This ion, if we count them up, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 positive charges in it and 0 negative charges. In other words, 18 protons and 0 electrons. The net charge on this atom is positive 18 if we were just using the non-units description, or if we were measuring in coulombs, 18 times 1.6 times 10 to the negative 19th coulombs. Now I can do this math out and I would be able to find out exactly how much charge this is, but for right now, positive 18 will suffice. Needless to say, this is a very strong charge. It's almost like a boss charge, almost like the boss of a video game level, the character that you have to defeat to win the game. This boss charge is in the middle of an open region of space. Now, let's take another tiny positive charge. I've labeled this magnet with a little plus sign on it. That's to show that this is going to be a little charge that is brought near the big one. Do you know which direction this little charge will feel a force? Well, it will actually feel a force directly away from the boss charge, up and to the left. That's because the small charge is positive, the big boss charge is positive, and since they're both charged positively, they will repel. But what would happen if I were to bring my small positive charge, my victim charge, maybe we can think of it as, closer to the boss charge? Well, you'll notice that it would still feel a force in the same direction, up and to the left, away, because these will still repel. But since I've decreased the distance, the force that they will repel with will be much stronger now, as indicated by the longer red arrow. So, as this positive test charge or victim charge moves closer to the boss or the source charge, it feels bigger amounts of force. What would happen, though, if our test or our victim charge was not positively charged? Let's say it was a tiny electron as represented by this smaller magnet. Would it still feel a force away from it? No, not quite. That's because since the test charge would now carry a negative amount of charge, it would be attracted to the big boss charge. In fact, with a very large amount of force. And that's because they are opposite charges, and opposites attract. So this little tiny test electron would feel a big force of attraction towards the big charge. And actually, the big boss charge would feel a force back, and they would be drawn towards each other. However, let's just focus on the forces on our little electron test charge for now. What though if I had moved the electron further away? Would it still feel a force? It would, but it wouldn't be quite as big. Since it's further away, it would still be pulled in because these are two opposite charges, but it would not be as strong according to Coulomb's law because distance and force have an inverse relationship. So what I hoped you saw in the last couple of sections is that if you have a very large source or boss charge, it creates this area around it that would attract or repel any positive and negative charges that would come in that region of space. All the positive charges would be pushed away, and all the negative charges would be drawn towards it. It doesn't matter where they are. If the charge is negative, it will be brought towards, and if the charge is positive, it will be pushed away. We in science say that this area around the boss charge is called an electric field. This boss charge has created an electric field around it that will repel or push away any other positive charges and will attract or bring in any negative charges. Before we forget about electric fields, one last thing. You may have remembered that as we got further away, the force became weaker. Electric fields get weaker the further away we get from the center. And that's because of Coulomb's law. As distance goes up, the strength of that force gets less. So the further you are in the electric field, the less force you will feel. So I hope you learned something today about electric charges. This is just the introduction to our unit on electricity. But it's important to know how to measure charge in coulombs, what kind of things have positive and negative charges, protons and electrons, and how we can change the electric force between two charges by either increasing the strength of the charges or changing the distance between them. And that was known as Coulomb's law. Now that you know a bit about this, we'll explore more about electricity in the rest of our unit. Thanks for watching.